Welcome to the trial lecture of Riccardo Simionato. On September 13th, 2024, Riccardo Simionato submitted the thesis entitled Neural Modeling of Musical Devices, Efficient and Low-Latency Data-Driven Emulation of Nonlinear Time-Varying Instruments and Effects, and sought leave to present it for the degree of Philosophia, Doctor of this university. The following evaluation committee has been appointed: Associate Professor Federico Fontana, University of Udine, Associate Professor Cumhur Erkut, Aalborg University, and Associate Professor Tesashvili Kelkar from the University of Oslo. And Associate Professor Tesashvili Kelkar has served as the coordinator of the committee. On November 28th, 2024, the evaluation committee reported that it had found the thesis worthy of being defended at the disputation for the degree of Philosophiae Doctor. The committee has decided on the following topic for the candidate's trial lecture: Audio Engineering Meets AI, Dataset and Model Lifecycles in Real-Time Small Models. Please everybody make sure your phones or computers will not make any sounds during the lecture. I now call upon the doctoral candidate, Riccardo Simionato, to give his lecture.
Thank you for the presentation. Yes.
Start with some feedback.
I can talk, yes. Okay, so I don't need to present me again, but good morning, everyone. Thanks for coming. The title of the trial lecture is Audio Engineering Meets AI, Dataset and Model Lifecycle, Real-Time Small Model. At the end of this lecture, we will have an overview of how AI and audio engineering can work together. You will see 4 different applications of the state-of-the-art that I selected. Subsequently, we will learn about research and development model life cycle, and we see when and why is essential to have small model and the main technique used to achieve them. Now let's introduce audio engineering AI, which maybe not all of you are familiar with both fields. So audio engineering is a discipline that encompasses the technology and technique used to capture, manipulate, and reproduce sound. It involves applying principles of engineering, acoustic, psychoacoustic, and digital signal processing. It addresses challenging and design solutions in sound recording, production, and reproduction. It's a profession that involves scientific, aesthetic, technological aspect, and engineering is both a research field and a field of practice. Artificial intelligence, AI, is a branch of computer science focused on creating a system that can perform tasks typically requiring human intelligence. These tasks can include decision-making, understanding natural language, recognize pattern, and more. AI aim to design machines that can learn, adapt, and function for solving complex tasks. AI has been around for a while when the computer was invented, and at the time the AI systems were designed by explicitly programming rules. But the recent trend consider models that can learn automatically for data. This approach refers to machine learning, which is a subset of AI that involves training algorithms to learn from and make prediction decisions based on data. Machine learning system use statistical technique to identify patterns in data and improve their performance over experience. For sake of completeness, deep learning is a subset of machine learning which employ more complex architecture and model. A model, in a broad sense, is a simplified representation of station of a system, concept, or phenomenon. In our case, the machine learning-based model will emulate a certain audio processing and will automatically build and optimize it using data. In our application, supervised type of training will be the majority, so the dataset will consist of input-output pairs. Now that we are on the same page, why we want to use AI. AI offers numerous benefits and innovation, enhancing creativity, efficiency, and functionality. AI can automate many tasks, routine tasks in audio engineering, for example, localization, mixing, can process and analyze large amount of the audio data. It can be used to create new sound, opening up innovative possibility in music production, enhance user experience, delivering personalized services. Okay, we finish the introduction. Now we will move on the rest of the lecture, which is organized in two sections. As an example of AI can benefit audio engineering, I selected 4 applications for the first section, which are not a comprehensive list because we cannot cover all the possible topic, but representative. The first application we will talk about is the automatic mixing. Audio technology has enabled music production on limited budget, but a skilled mix engineer still needed to deliver a professional standard material. So the goal here is allowing people to access good mixing also at home and improving efficiency for audio engineering, helping to fasten repetitive tasks. Now we listen some audio example with the objective of understanding what is mixing and how modern AI are able to accomplish this task. And we follow this pattern for all the video I will show you, so also later. Sorry. Okay, now that we have an idea, what we want to do is we want to estimate feature from different stems and compute the FX parameter or automatically generate the mix audio track to balance loudness, dynamic, avoid frequency masking. For example, we want to, here you can see the mixer image. We want to estimate the parameters including this mixing chain, let's say. Among not machine learning approaches, we found rule-based cost-adaptive mixing effects. Rule-based consider in rule-based system parameters are continuously smoothly adjusted to match a given criteria. While in cost-adaptive filter, features are extracted from the stems, as you can see from this image, and influence the digital signal processing algorithm that filter stems individually. While among the machine learning approaches, common is to process directly stems from using in the time domain, using convolutional neural networks, also autoencoders, and optionally, some condition control can be given, usually define some terms indicating an abstract meaning and ruling to what extent the mix should be, for example, warm or dark or bright. Another approach consider estimate the coefficients for a digital mixer. So we will output the parameters for the dynamic range compressor, reverb, and so on, equalization. Other works involve applying the chain of effect, but consider just one track. So in this case, the guitar, we want to apply to a clean guitar a chain of effects. And similarly, before we can be done in time audio domain or outputting the parameters for a chain of predefined effects. Another interesting application can be we want to know exactly what effects have been applied, what order, to achieve a particular sounding. This can be done using extracting feature from the input audio, and in this case, more is a classification problem, which will output the label of each effect. We can find plenty of AI commercial products. Popular one are Ozone by Isotope. Then there is SmartEQ, SmartLib by Sony, but there are many. The second application that I will talk about is source separation, which is the opposite aim of what we have seen before. Here we want to recover the individual tracks or stems by a mix. So the sources are predefined, and most of the time are bass, vocal, guitar, and keyboards. Depends on the dataset used, but mostly biased on Western music. In this case, there is not equivalent to the mixer to do the source separation, so it cannot be done with analog processing, while mixer can be done. Possible application here are audio editing, sampling and remixing, spatialization, and upmixing. Again, some audio example to have clear what we are talking about. Here, not a perfect separation. So, common approach before machine learning is achieved through linear filtering, which exploit knowledge of spectral properties of the unknown signal. The estimation of this property are the main challenge, since they are not available a priori, but instead the only material available is the mix. Regarding machine learning approach, one of the first approaches considered to output the power spectral density from taking as input the frequency information of the mix, which will be used to perform the linear filtering and retrieve the individual tracks. Subsequently, have been seen more effective outputting directly the spectra, so then doing the inverse transform to achieve the individual stems. And to mitigate the issues that can derive from using frequency domain, less flexibility and phase issues, some proposal work directly in the time domain using convolutional UNet neural networks, which will take as input the output directly the raw audio. Then we can combine both the frequency and the time domain in order to mitigate both problems. Also here we have some proposal, commercial products. I pick up remixed by Acon Digital, which split the different predefined sources. or DJing application, for example, DJ Prof by Serato. Also, there is some cloud-based services which offer sound separation. Hans, Lalay are two examples. Okay, now the third application is audio repair, which will refer to noise reduction, the clipping, in painting, bandwidth extension, voice pitch correction. In this case, we want to retrieve the clean audio from a corrupted one.
We will glow in the dark, turning dust to gold. We will glow in the dark, turning dust to gold. We will glow in the dark, turning dust to gold.
Yeah, sorry, I started too early, but yeah, this is an example of one audio repair, the other is tuning. In this case, there are several traditional approaches for noise reduction, spectral subtraction, linear filtering again, or wavelet-based method, also statistical approach, for example, Kalman filters. Then for audio restoration in general, probabilistic modeling have to be used, autoregressive modeling, optimization-based techniques. While for machine learning approach, convolutional neural networks have been popular, being effective at capturing localized pattern in the audio spectrogram, making them suitable for separating noise and the audio components. Or autoencoders. Here the idea is to learn a compressed representation of the input signal, removing the redundancy and not essential feature, for example, the noise. And finally, among the deep generative models, diffusion have been emerged as powerful technique for learning complex data distribution, so it's mainly used for restoration in painting and the clipping. With diffusion, there are not distribution independence assumption on the signal, and they're usually working considering the constant Q transform and spectrogram domain. Instead, for pitch correction, usually is involved in 3 stages, so pitch detection, wave manipulation, stretching, or other technique, and then resynthesize the full waveform. And in this case, for machine learning approaches, have been proposed conditional variation encoder, exploiting the mass spectrograms. Sequential recurrent neural networks just for the stage of the pitch detection. One combination between transformer and generative adversarial neural networks, which transformers predict the pitch and generative adversarial neural networks synthesize the waveform. And again, diffusion model being particularly effective also in this case. Here, among the commercial AI-based product that can be found, there is the famous RX by Isotope, which deal with the clipping, the popping, and everything related to audio restoration. Audio denoise by Crumble Pop, which is a noise reduction, and repitch from Synchro Arts. Again, as there's cloud-based services, which done also this one, sound separation, noise reduction, and restoration. The last application I have selected is effects instruments modeling. Here, we want to apply, we you want to emulate all the analog gear and instruments, which can be appealing for mix engineer, for example, to apply during the mixing studios, and which offer particular warm and vintage sound, very appealing nowadays. But these effects on instrument can be expensive, big, with limited accessibility. So here the aim is emulate this sound in the digital way. Again, some example, one from the analog effects and one from acoustic instruments. Okay, so usually here the emulation rely on external information. It can be physical or just trying to emulate the sound characteristics. But with the advent of machine learning, usually we collect the recordings from the device, which and then we use our neural networks we train a neural network to emulate the same audio processing. Starting with normal fully connected or convolutional neural networks, common methods after that was using black box recurrent neural networks, where also the various effect parameters have been included as well, using a specific technique. For example, the parameters are processed by a neural network, which output two coefficients that are used to modulate the internal representation of the input signal. Or this is more common for instruments, but also for other overall effects have been done. We output the parameters that use for synthesis algorithm that use to synthesize the sound, the final sound. Here, commercial products are mainly based on distortion units. So we have the guitar rig from Active Instruments, but also Taper from Baby Audio that emulates tape recording, and Neural DSP that is focused on distortion pedals and preamplifier. Okay, now we have moved to the next part. We have seen 4 different applications, and now we present the model life cycle to design a small model efficient solution. Let's reflect first on the application we just reviewed. In terms of requirements, real-time low latency. Latency is the input that the system takes to respond to an input, the delay that is to do to process the audio. In the case of automatic mixing, real-time latency requirements are context dependent. Depends on if you're in a live situation, it is crucial. But there are also situations where mixing studio that offline rendering can be acceptable. Real-time capability nowadays, considering the research, are available, but low latency is more difficult to achieve. For source separation is not fundamental, but if we have, why not? So can be desirable. Here the network particularly large, so real time and low latency are difficult to find. Audio repair again is context dependent, depends on the application. The noise reduction can be desirable to have real time, but if you consider restoring audio historical track, can be done offline. And also it depends on the solution that you use. Can be some solution of real time, but for more complex, effective network, for example, the diffusion one are more difficult to find, and especially for low latency capability. Lastly, for the effects instruments emulation, I would say that it's very important to have real time to be playable. And in this case, we can find several solutions with low latency real time capability. Now let's introduce the model life cycle. It refers to a series of stages that a model undergo from the conception to the deployment. So we have task definition, data collection, design implementation, training, evaluation, deployment, and maintenance. Here are some stages can inform some previous stages, optionally. So in the task definition, we want to identify the task the model to accomplish. This includes understanding the objective, the constraints, the outcome, which will influence also later the development stage on the select of the architecture, which depends on the problem of the study. Also, in this stage, we want to identify the data to be collected and the data accessibility. Data collection is a crucial aspect since the quality of the model strongly depends on the quality of the dataset. And we want a dataset that is relevant, so with a representative example for the task that we want to accomplish, consistent with a consistent formatting labeling. We want high quality recordings with a sufficient quantity of example. This depends on the task we want to accomplish. Diversity, so diversity balance, so a wide range of different scenarios, but equally also represented. And finally, well documented. Another important step is the design and implementation. Here we have to choose the appropriate algorithm or framework to develop the model. Topology of the network of type layer are of different size can have a huge amount of different combination. We cannot try them all, so we need to find a suitable solution in a reasonable amount of time. Generally, we use for this purpose framework that are specifically designed for that. So, for example, PyTorch, TensorFlow, that are high-level programming language that allow us to design and train the networks in a very fast way. When we find the suitable architecture, we need to optimize also the training stage. So here it involves selecting optimizing the parameters, for example, the batch size, mini batch size, depends what we are working for, learning schedule, and loss function, for example. Also, the selection of loss function is important since this is the aspect that the process will try to minimize, so the aspect that the emulation is minimizing. And after that, we have to assess our model performance. So using metrics that are relevant for the problem domain. This step have to ensure the generalization capability of and not seeing data, and need to assert the main, the more critical aspect depends on what we want to accomplish. For example, the time domain, frequency domain depends on what is the outcome. And also, perceptual tests are, of course, important since we are dealing with audio, and the perceptual feeling is a crucial aspect for the final application. Lastly, when we have trained, we achieve our model, we need to deploy the model in a production environment. As I said before, we usually use high-level programming language, TensorFlow, and PyTorch, or anyway, Python, probably inside Python. But these are not efficient. I mean, if we want to stay in a cloud-based application, can work, let's say. But in case we want to deploy the model in something usable in a music context, for example, VST, we need to port the Python model into a C++ model. So we need to port, to convert from Python to other low-level language programming. And this we will see shortly, some option that we have. But another crucial aspect that we have to, the VST will run on a CPU simultaneously with other software. So I have to share CPU and memory with an undefined number of other processes. Lastly, for the maintenance, we have to remember that the model will compile for each architecture and different operating system, which change over time, and then we have to update our application to avoid to become obsolete or to not be more compatible. So where we must consider this aspect: task definition, design, implementation, deployment, maintenance. Now we see how to reduce the size of the model to achieve a small model. Having a small model increase our chance to find an efficient real-time application, which also will depend on the device that we are going to deploy the application. So how we can get small model from the design? We can consider doing the training or post-training technique. Design is because we can consider to give external information to our model in order to reduce the effort from a neural network and optionally and possibly reduce the size of the network. This can be also efficient in case of limited data scenario. But we have to remember that this adds constraint to the model, which can affect accuracy and limit the learning capability of the model. Then during training, we can consider distillation knowledge. The idea here is from a pre-trained, more complex model, that is, will be a teacher, we want to distill its knowledge to a smaller model, which is our goal model, which will be a student model. Here, the idea is that the teacher model can digest better data set and make it in a more comprehensive way, understandable way for the student. And can be done, there are two main options, response-based and feature-based, where response-based include giving the output of the teacher model to the student model as a soft label, or feature-based, where we try to distill how the teacher model extract the feature among the layers. And this can be done offline. There are some solutions so online, so you train simultaneously, or self-distillation, where the teacher and the student are the same model. Yes. So you try to distill the knowledge that acquired from the later layers into the earlier layers. Finally, there are three methods to consider after training. Quantization reduces memory usage. It adjusts the numerical precision of the parameters and the computation. So we reduce the number of bits used to represent model parameters activation. This can bring beneficial, but is strongly art dependent. So that it may reduce memory, improve the computation speed or energy efficiency. But of course, we limit the range of representable values. This can introduce rounding errors, affect the accuracy, especially for autoaggressive frameworks. Then we have pruning, which is based, in this case, we remove parameters that are only a minor impact on the accuracy of the network. So here we do an iterative search in order to remove connection or the wall neurons, and in the same time have just a minor impact on the accuracy. Optionally, can be we can remove the weights of the connection, the neurons, but also the layer, depends on the situation. This compress can compress the neural networks at the end. Lastly, low rank factorization. Here the idea is to approximate tensors that represent the wave and the bias, which are high with high dimensional tensors. We want to approximate that with a lower dimensional tensors. This can improve storage or inference time, but depends on the architecture that we are considering. For example, fully connected layer can improve the storage requirements, but evolutionary networks have seen improve also the inference time. But it's quite complex to implement. Finally, also, if the model is small, it will be not efficient if still implemented in high-level program language. For example, I said before Python. So there are frameworks which allow to convert the machine learning model to a low-level programming language, which can be compiled, applied to some other, can be used with. We can offer other hardware optimizations. So we have light runtime, that is the new TensorFlow Lite, which have to convert from Python to TensorFlow, also JAX is another framework, machine learning framework, to a small reduced format for the model. And Open Neural Network Exchange is another framework developed as machine learning converters. In alternative, a more efficient way can be re-implement the model using C++ directly. For example, in this case, we have a already developed library, RT Neural, which is specifically designed for real-time audio. The idea was that the major neural network libraries are typically considering applications such as computer vision or natural language processing. And so the optimization involved more larger networks than the smaller one. Also, since not considering real-time audio, this library can perform operations that are not so desirable in audio context. So this library is a C++ library that is designed to perform specifically real-time audio rate inferencing operation per pre-trained neural networks. Here, since it's a work in progress library, maybe not all the architecture are already available, especially the state-of-the-art proposal, but yeah, it's still a work in progress, and step by step is going to be expanded. Okay, so we have also covered the last stage. So we have seen all the life cycle, and we are going. We have seen also the stages, and where in the stages is important to consider if we want or not a real-time or efficient final application. And finally, we have seen some main optimization techniques that can be applied that are complementary, that are not replacing each other. You can find a combination and try to reduce as much you can your model. And finally, we have seen how some possibility that we have to deploy our model in low-level program languages. And finally, build our application that will be compiled for different devices and different hardware scenarios. Okay, so what we have learned, we have got an overview of AI, how AI intersects with audio engineering. We have seen the state of the art for audio engineering applications that are representative for a real-time context. We have seen what's mean life cycle, such as the development life cycle for a model, all the stages, and where understand all the various steps that we can take to optimize it and find efficient solution. So a small model in real time. Thank you.
Thank you, Riccardo. Is this on now, or did I turn it off? Yeah, it off. There is now a break for about an hour and 15 minutes. The disputation will continue here at 1:15. So please be in your seats in good time before it starts. Thank you. Welcome to Master Riccardo Simionato doctoral disputation. On 13 September 2024, Master Riccardo Simionato submitted a thesis entitled Neural Modeling of Musical Devices, Efficient and Low Latency Data-Driven Emulation of Nonlinear Time-Variant Instruments and Effects, and sought leave to present it for the degree of Philosophia Doctor of this university. On the recommendation of the Department of Musicology, the Faculty of Humanities appointed the following evaluation committee: Associate Professor Federica Fontana, University of Udine, Associate Professor Timur Erkut, Aalborg University, and Associate Professor Tesashvili Kelkar, University of Oslo. Associate Professor Tesashvili Kelkar also served as coordinator of the committee. And on the 28th of November 2024, the evaluation committee reported that it had found the thesis worthy of being defended at the disputation for the degree of Philosophia Doctor. Earlier today, the candidate gave the prescribed trial lecture on the following topic: Audio Engineering Meets AI, Dataset and Model Lifecycles in Real-Time Small Models. The trial lecture has been found satisfactory by the evaluation committee. Today, the candidate is to defend his thesis in public. The first opponent in the disputation will be Associate Professor Federico Fontana, and the second opponent, Associate Professor Timur Erkut. Should any person present wish to speak as an opponent ex auditorio, notice should be given to me before the second ordinary opponent is called upon to speak. Only the in-person audience can ask questions ex auditorio. May I kindly ask the audience to turn off your mobile telephones? And then I call upon the doctoral candidate, Riccardo Simionato, to come forward, well, you're already forward, and give his introduction.
Okay, the microphone is... Okay, perfect. So, good afternoon, buon pomeriggio. Thanks for being here. Now I will present and defend my PhD thesis with the title Neural Modeling of Musical Devices, Efficient Low Latency Data-Driven Emulation of Nonlinear Time-Variant Instruments Effects. With musical devices, we refer to electro-mechanical devices such as analog synthesizers or effects, or acoustic devices such as acoustic instruments. In addition, we can distinguish into two categories: processor and generators, where processor alter a sound signal and generators create sound from the direct energy, transfer of energy between the musician and the instrument body. Why we need emulation of musical devices? Well, they can be the hardware or acoustic instrument can be expensive, large in size, difficult to obtain from the market, and in addition, digital emulation can offer new, novel, open interaction capability, which can be appealing for artists. Emulating musical devices, dynamic area of research from the 90s, which is characterized by significant scientific relevance and artistic implications. Emulating musical devices is not trivial. They may present nonlinear, time-dependent behavior, which means that that describe a complex equation and present a time-dynamic behavior. In addition, they may feature simultaneous multi-control parameters, meaning that the emulation have to offer the same simultaneous and continuous control over the audio generation. In addition, musical devices have to be act as real musical devices, so interactive, offering the same physical inputs that you can find from the real counterparts, low latency, so update parameters, these inputs parameters often enough to be perceived as continuous sonic variation, and working in real-time constraint. So nowadays there are advanced techniques to emulate musical devices, and several products can be found commercial in the market as well. In particular, we can distinguish between two main approaches: physics-based and data-driven, where physics-based start from the knowing of the inner mechanism ruling the device functioning, and data-driven rely on the analysis of measurements taken directly from the device. Physics-based can lead to high accuracy, allow flexibility, easy changing of internal model parameters, but require to find a stable commutability scheme, which may lead to computational cost and or approximations. In addition, they are device-specific, and the information of the music device must be known. For example, the input circuit scheme or the material values for each component consisting of the musical devices. On the other hand, rely of the measurement taken from the device eliminate the need of specific knowledge. As we can see here, we need the input-output pairs collected from the device, which we can give to our data-driven algorithm, for example, in our case, machine learning, which will produce our emulation of our digital emulation. Data-driven methodology rely on dataset, means the quality of the model strongly depends on the quality of the dataset, can lack of interpretability, so it can be difficult to change internal model parameters, and approximate a continuous function based on a limited amount of recorded examples. A popular data-driven methods is based on artificial neural networks, which is a machine learning algorithm inspired by human brain. Are networks of interconnected neurons organized in layers, which internal parameters are optimized through optimization process called training. Neural networks offer advantages over traditional data-driven methods. They offer a robust framework to model all the device components in the same time in an automatic manner. They also present less sensitivity to noise and extract informative presentation from data, which help to generalize predict accurate prediction also for new inputs. Regarding emulating musical devices, success has been made with amplifiers and distortion units, but limitations still are present for devices with more complex behavior, in particular with time-dependent behaviors, which imply tracking the past input information and the past information of the system, which hinder the design of real-time and low-latency solutions. In order, limitations are present also when considering a large set of control parameters, which need a specific technique and add complexity. Regarding generators, primary investigation will be made for acoustic instruments. For example, acoustic drum emulation will be made also in real time. But limitation may be present for acoustic instruments with more complex harmonic structure and stimuli, which playability is still limited. All these considerations lead to the following aim. How can neural modeling techniques be extended to emulate complex musical devices while retaining the characteristics necessary for a playable emulation? This in turn leads to three research questions. The first one is, how can we design neural architecture that can be trained to emulate time-variant and nonlinear musical devices while satisfying the latency and rotational requirements of digital musical devices? The second one, how can neural models of musical devices be conditioned to adjust their response according to the inputs, such as control parameters or stimuli, enabling interactive user control? While the third one is to what extent are this neural architecture or their internal component sufficient generic to model behavior within or across different type of musical devices, and what opening the neural modeling can offer for conceiving novel creative devices. The methodology to answer this question represented here. First, a representative case is selected, then the data set is collected, the architecture designed, trained, evaluated to find the optimal solution. The methodology presents an iterative nature, meaning that every stage can further inform one of the previous stages. And since, as we said before, we can distinguish between processor generators, we select a representative case for processor and one for generators. In the case of the for the processor, I selected the optical dynamic range compressors, which are a device with nonlinear response, long transient, and time varying input-dependent parameter, which is the internal gain. The datasets are collected directly from commercial products available here in this building, which are the TubeTech CL1B and Teletronics LA2A. After 3 years of experiment and design, I developed neural networks based on states, which help to encode past information of the input signal and of the neural network itself. All the possible control parameters are included using a specific technique. And the proposal model architecture were evaluated based on quantitative metrics and perceptual test, and were compared with variation of the proposal and the state-of-the-art architectures. Finally, the architecture working in offer real-time capability, low latency, and working in 48 kHz. Now I will play for you some of the example, some results from this study. Okay, so we have seen the case of the processor case. Now we let's continue with the generators representative case, which is the acoustic pianos. Dataset in this case were collected from this clavier, like the piano that is present here, and from online database already existing. And the dataset consists of single notes and chords. In this case, we took a slightly different approach, given by the fact that for generators, the input and output rely on different domains, symbolic and audio. So instead of predict directly the audio sample, we predict the parameters, which they are given to a algorithm that generates the final sound. And this algorithm is designed using physical information. The experiment led to split the model in 3 components: harmonic, transient, and noise. Harmonic described the temporal evolution of the frequency components. The transient is the initial percussive and harmonic part of the note, which is given by the strike of the hammer. And the noise can be is the residual of the composition process, which is associated to the background noise. Also, chord modulation is included, which in the reality the sound of the chord is not corresponded to the simple sum of the single notes, but there are some coupling effects. In this case, we consider this situation as a processor, so we process the sum of a single note with a neural network in order to give the sound of the real chord. These represent a novel approach, so it's not easily comparable with the state-of-the-art data-driven approach. But again, the evaluation is based on quantitative metrics, listening tests that highlight that the model captures the characteristic of the piano, and also the modeling of the chords gives some better perceptual results than the straightforward sum of the single notes. The sound is less convincing of the state-of-the-art neural network architecture, but presents a significantly less computational cost and latency. Again, now we will listen the example for this case. Maybe. Okay. No, so. Okay. So this work was carried out for in 3 years, where several articles have been emerged, 11, which among of them 9 are peer-reviewed, published. And to answer the first question, state-based neural networks have been seen effective on encoding the past information of the signal, have been accurate and help to keep the number of parameters significantly low, and offering to work with a small window of input. Although transient represents a challenging scenario, which the architecture neural networks have struggled on emulate abrupt change of dynamics. In both the case, the control parameter or possible stimuli have been included. In particular, method based on modulating internal representation of the input signal have been resulted the most effective, and here nonlinear modulation could further improve the case, but further experiments are needed. And lastly, similar architecture have been able to model devices inside the same classes, so different dynamic range compressor, different acoustic pianos. And in case of the processor, have been effective also for different classes, although not all the classes not all the audio effects. Also, neural network has been seen a nice approach to conceive newer musical devices offering creative feature, novel creative feature. To conclude, the contribution of my work are deep learning technique, including specialized architecture, approach for model devices presenting linearity and time dependencies to achieve low computational complexity and minimal latency. Approaches to condition neural models according to the input and/or stimuli, knowledge on the use of hyperparameters and loss function for training parameters audio to audio or symbolic MIDI to audio neural networks, and following the open science principle or the source code, public data set model, training procedures associated training models are available online to allow reproducibility. Thank you.
Thank you, Riccardo, for this introduction. We will now have a short break of 10 minutes approximately. So the proceeding will continue at 10 to 2. So. Call upon the first opponent, Associate Professor Federico Fontana, to come forward. You're already forward. You can sit down, please, and we will continue.
Thank you, Professor. Good afternoon, buon pomeriggio. I really thank the University of Oslo and people who are here to make this event possible. It's really great to be here now. And now it's my turn to honor my duties, and I hope to be thanked in the end as well. So, thank you, Riccardo, for summarizing your thesis. It has been absolutely necessary to do that. And I would start with one question that was not sure whether to issue it or not, but then I saw that you repeated this at least on 4 slides in your presentation today. That was slide number 2, I think number 5, and the slide before the last one, and the last one. And this is about the concept of time variation in the effects. So my first question is that I would ask you, what do you exactly intend for time variation with the formality that you think is worth? And how do you define a time variant or time varying audio effects?
Thank you for the question. Thank you to allow me to clarify this aspect. Yes, you did right. The first revision of the thesis was some ambiguity on that. With the time, I dissociate time variant system with what we report as time variant instruments and effects, meaning that the aim of the study is to focus on devices which present a time dynamic evolution, which particularly present parameters, internal parameters on the functioning that change over the time, and which may be dependent also on the input. In case of the compressor, we have the gain that is dependent on the input and the previous states of the musical devices. While also in piano you can find parameters that change over time. So we define time variant instruments in a different, not associating with time variant systems, which, yes, is a different concept.
Yeah, in fact, I saw that you partially resolved this ambiguity in your thesis, in your latest version, and but still there are these 2 sentences. One is at page 72 that you say responding to inputs in a nonlinear and time-varying manner, and this matches with the explanation that you gave it now. And yeah, and at page 65, yeah, when you said they exhibit time-varying gain factors that can have complex profiles. But then if I would ask you to define a time-varying system with in a more formal way, so with if I would ask you, how would you define a time-varying function? So we consider an effect, so the input X, output Y, and how would you write it down using one scalar function, linking the input signal to the output signal, if this effect were time varying?
Yes, first of all, let me say one thing, that we also clarify the differences between time variant system before, like, we clarify that we don't meaning the classic way of time variant.
Okay.
Now you ask me of our time variant instrument effects or the classic, because in our
Well, classic for me means the mathematical definition of a time varying system, maybe one-dimensional. You can even elaborate on the classic definition, maybe with just one formula, or with what you call your own definition.
yeah, because in our case we
Sorry, no, I'm sorry. Yeah.
no, please, please.
No, I'm very sorry, but just to see. No, okay. No, because my son is around.
Yeah,
also,
I imagine.
so
Yeah,
it's
don't worry.
just- okay.
Like in the case of the, for example, you take the compressor here, you have the output depends on the past windows information of the input signal and on the past states of the compressor itself. So it's true that if tomorrow, in isolated way, if we take on the rest the compressor and tomorrow we play the same things, we have the same things.
Yeah,
But to
exactly.
present attack and release, or anyway, a changing, a varying compressor way that depends on the on the past information of the signal and how was triggered before the compressor.
Yeah, but I think you agree that once again this is not time variation. So we can oppose further on this point, but I think that in a system sense, so a time varying system is a system that tomorrow will behave different than today. So a time varying system is a piano that's tomorrow has not the same intonation as today.
Yes.
But as far as you don't change the parameters, or you change the parameters of an effect, then the system behaves with that set of parameters. So in this sense, it's a dependence on the parameters, or a dependence, of course, of the input signal, but not a dependence on time. So I think you should be careful before writing time variant systems.
Yeah, I agree, and for this reason, on the revision we clarify that we don't mean the classic time variant system, but we give an hour, let's say, definition on the scope of the thesis to solve the ambiguity.
Okay, so it is enough with time varying stuff. Then I have another question that now is at page 78 of the yeah 78 of the thesis, and my question is about the piano recording and the acquisition of the data set. And my question is, why did you use one microphone for acquiring the recordings from the piano?
Because at that stage, I know that there's also the room effects on the stereophonic feature of the.
But even if we work in an anechoic chamber, why would you use one microphone for recording the piano?
The recordings have been made for 2 octaves, and for the purpose of the study, we consider enough to have a mono signal. That data set that we collected was for the emulation of the piano. So we, in any case, we were like outputting where we wanted to assure that the model could reproduce the partial evolution and so on. And then we use for the paper, the comparative study, which was to we compare with other monophonic recordings. So the wasn't on the purpose the stereophonic aspect.
Yes, it is, but the point is that if I choose one position, say, and then I play, point is that if I'm listening from here, I listen to one sound, but if I'm from there, then I'm listening to another sound.
Yep.
And if I move farther around the instrument, then I will be listening to different sounds depending on the radiation field of the piano and the other factors that, well, this is more similar to a listening room. But even if you go to an anechoic chamber, then you hardly collect a piano sound, or you can hardly summarize the sound of a piano with one microphone.
We took from the piano that was recorded was the upright piano, so we place the microphone near the anyway in proximity of the strings in order to catch the sound directly from there.
Yes, so this is exactly my point. So as close as you put the microphone to the strings, then the more space dependent becomes the sound. One choice for choosing one position, for instance, the cases when you choose to record a piano with one microphone is, for instance, if you want to simulate the pianist listening point, so you can just put the microphone, say, more or less here. That makes sense. But if you, go around the soundboard with the microphone, then I think at least, so if you don't have a microphone array available, then one should at least try different positions with one single microphone, and then maybe later make a blend, make a mix, or make whatever. But starting with one microphone is similar to have a small ensemble, so a band playing and putting the microphone in the center of the band and get the take. So.
But still, since the piano was an upright, we collected just one octave.
Yeah, but also the upright pianos has a kind of diffused. By the way, the upright piano is the one for which there are reliable studies about the diffusion because the modes, the vibration modes of the soundboard are known better in the upright piano rather than the grand piano. And this is also because in the grand piano you have the diffusion from the lead, and so it's more difficult to characterize a grand piano from recording. But the upright piano, there are several studies that explain how sound diffuses from the vertical soundboard, and so I think that in that point there could be maybe a better time in spending some more time with the recordings and maybe then deciding how to mix.
To build up on that, at that stage, we try to remove also the room effects and everything, and we for the pupil of our study, we selected one microphone. That you said, I agree, and this actually is something that I performed later when I arrived this piano, and I had more room, more possibility, more microphones. In that case, we use 2 and 2 microphone in order to have a better data set that hopefully will come later and so on. But for that specific timing, we removed all this aspect.
Okay. Yeah, no, that was also because I was listening to the sound examples, and there's a flavor of one mic take. I don't know how to explain it. It's kind of some lack of crispiness in the sound that couldn't be the neural network's fault, but just the flavor of the recordings that you made.
You are pointing the single notes or the chords?
I was listening to the single tones.
Because single actually wasn't.
It wasn't your.
It wasn't mine. It was
okay.
actually from you. The database that you made with
the
Papetti.
ZEB database.
Exactly. That of course I rendered on mono that as well.
Yeah. Okay.
But that one started from I think.
And so in that case makes sense because the BVIP database was collected from the listening head position, and in that case you have this kind of smoothing because of the position where the.
Yes, to continue, the data set was quite complex to find a proper data set for the study and so on. Also for this reason, I came up to take the database online in order to make better, more strong the stuff.
Yeah. Okay. Yes.
But this is a limitation of my data, my first data set.
Okay. Yes. Well, recording a piano is always a difficult issue, and okay. So this brings me to the next question. That is again related with the piano, and let me see. And it is related with another project that I followed years ago. That was when we designed and then had realized the physical model piano, physically based piano model that then went to production also. And one thing that you say here, page 79, is when you start, writing about the manifold effects that the piano can produce, and especially you are referring and paragraph before the last paragraph at the middle, page 79. You say key coupling and restriking aspects that sample-based methods struggle to accommodate due to their high memory demands, and this is certainly right, can be emulated with the addition of small auxiliary networks without notably increasing the system's complexity, and this might be a matter for the second opponents of Schumur. But then I would like to point out the end of this sentence when you say, unlike with physical modeling methods. What do you exactly mean with unlike with physical modeling methods? So you mean that physical modeling methods are not able to model key coupling and restriking?
No, I don't know if you, before what you say commercial piano, you mean about piano tech, but in general, considering literature, I think you can add this coupling and restraining situation, but add significant complexity on the description of the problem, and also because especially for the coupling, I think find a proper scheme. Probably have some coupling or linear interaction between equation, find the solution and so on. I think they add particular complexity.
Yeah, that is.
That of course some years will be advanced, will be easier.
But you mean in physical models?
Yes, physical modeling.
No, I have to contradict. No, this problem was solved about 10 years ago with the physical model that led to the physics piano made by Viscount, and in that case the underlying model that was a research from a group that was led by myself and involved Balázs Bank and other researchers that you actually cited in the thesis here. In particular, I refer to yes, exactly. So page 110. So Balázs Bank, Stefano Zambon, of course, and myself, a model-based real-time piano synthesizer, where key coupling and restriking were solved in physical terms, so in physical modeling terms, and key coupling. Basically the two of them. So the idea was that of having several, in the beginning was several 100,000, then there was a pruning was made, and in the end it was some thousand resonators, that of course you know what is a second order digital resonator. Yeah, I'm sure you know that.
Yes.
Yeah, okay. Always running in parallel and simulating all, and modeling all the possible modes of a piano in a continuous real-time run that was implemented by one processor that could afford that. And what happens with string coupling? Well, it simply happens that since all the resonators are always running and tuned, of course, then if you play one note, then you hear one note. But if you have the other resonators that are running, so like in this, now they are running, but you hear nothing. But then if you play the note, and this is the string coupling, has been solved in physical modeling. And the same thing is with restriking, because you know that the original wave digital hammer designed by Scott Van Dyne and Julius Smith solved the problem theoretically, but then it came to one evolution and an algorithm that could implement that. And once the digital hammer was coupled to this huge bank of resonators, then it made the job of solving the restriking problem that we know, you know. That we all know. So every hit is different from the previous, but it's not time variation. It was not a time varying piano, definitely. Okay, so I think that's. So, do you agree with these considerations?
Yeah, of course, I agree on the paper, but it's in what will mean that is actually adding some complexity that can be, in any case, maybe avoided. In the case of model synthesis, you add you pre-compute the nodes, or depends also to what extent the accuracy of the emulation, basically.
Well, the physical model in that case is just transformed in a model system, in a model synthesis algorithm, but there's no addition of complexity, basically. There's no more complexity than a normal physical model, and so a well-designed physical model accounts for restriking and key coupling. It was probably even born to overcome the limits of sampling. So if digital modeling existed, was basically to try to cope with this kind of effects that we know that sample pianos cannot reproduce. So in this sense, I would say that I wouldn't be detrimental with physical models because they cannot simulate the effects that they were born for, basically. So this is the important point, that plenty of research was spent in physical models to try to get those effects. Otherwise, we rely on excellent samples, and that's it.
Yes.
And this would lead to my next question. That is, let us hear to one sample. So one piano tone from your model. Maybe, I don't know which one. So I'm not a good pianist, so I would be probably not able to hit the right note, but let us choose one and let us listen, and let us engage ourselves in trying to make a criticism at runtime of the differences.
Here I have the page with the example, real and the modeled one.
Do we have the classic A4? 400, that should be...
Yes.
Okay, so let's start to make the comparisons and let us try to issue them. So let's start with the pianissimo, or the softest note that you have.
The notes are played on the test set, which are the medium velocity.
Okay, so we have
should
medium.
be 40.
So we have a mezzo forte, or kind of.
Yeah.
Can you turn up the volume a bit?
Here is the max.
Okay.
I don't know.
Once again, please. Which main difference?
This is
We can alternate a bit. You can just play, then I play, then you play. Yeah.
Firstly, brightness. This is also downsample.
I think the first difference is in the attack.
Also, yeah, of course, the attack.
I kind of sensation that, so you have a post network adding the hammer noise, I guess.
It's a sum of...
it is, yeah, I can hear the sum. I think the audience can as well. You will hear something like, try to, again. So you hear the hammer, and then you hear the notes. There's the sum. Maybe this noise I can be able to emulate by doing a fortissimo, maybe. But then there's the transient nonlinearity, but you don't have the different dynamics. You have only this one.
Yes, in this case, yes.
Okay. So, okay, but of course you know that if we go from the pianissimo, oh, sorry. So there's a word of sounds that we can get out from the piano. And, but I mean, it's a very good result, I think, that you were able to.
I think the strong point is also considering the complexity and the size of the networks in order to, because there are the other one model that is particularly larger than, I don't know in this case, because there are more, the dataset in that case, the maestro dataset, so it's a sonata basically, and I don't know how, there are not singular notes to evaluate or to anyway to.
Yeah, no, I mean, this was just reminds me when I was working on the project for designing the physical model that we were positively going to the golden years of those who had to inherit the project, and we were regularly kicked out with and deflated completely with our sounds, and this was lasting for months, I mean, or for almost 1 year. So I mean, approaching the the level, the excellence in musical instrument sounds is really a hard task, and this is just what I would I'm not going to deflate this project. I mean, I absolutely I consider it a great advanced in state of the art. But of course, you know that there's always a long way to approach the level of the real instrument, provided that nowadays one wants to approach it, because, yeah, who wants to listen to a good piano? This is another question. Yeah, and okay, so how much time do I have? It's 25 minutes. 25 minutes. Okay. So then I would try to move to the realm of neural networks. But I mean, arriving from a musical viewpoint, then I will let the more technical stuff to the second opponent. But while being, say, on some musical considerations on the use of neural networks and their importance in a way, the context that they can, the place that they can have in the design of tomorrow's musical instruments. And so let me start from this consideration. Okay, so one possibility is to say, okay, I have this beautiful piano, then I build my gigantic data set, my colossal data set, then I feed my enormous, super powerful neural network, and then eventually, say, we will approach and resemble, and then the golden heirs will be finally won, and they will say, okay, your model is perfect, and it runs on a cluster of or on a mobile phone, then depending on the computational resources. But I would like to try to start from a different point. I was also talking maybe yesterday evening about, or no, this morning with Alexander of this learning by doing thing. So we have two possibilities. One possibility is, it says, to start with a robot, so with a humanoid, and providing him every sort of knowledge, so kind of a parallel of feeding a network with all the knowledge that we can extract from a piano, and let it swallow everything, or start, say, with a humanoid robot, just to making a parallel and putting into it the whole knowledge possible, and then it will do everything perfect, as well as the network will. But let us change viewpoint, and let's move to the viewpoint of a musical instrument builder or a musical instrument designer. So we let us think about, I don't know, Adolphe Sax or Bartolomeo Cristofori or well, Stradivari or Bob Moog. When they were in front of discovering something new, and they had probably, I think, they had no clear idea of the sound they wanted to achieve, or they wanted to, but they had one idea in their mind, and they had a background. So my point also is contaminates with the idea of having, of building new knowledge by doing. That is basically what's the human nature we are. So we build something new. So your thesis is something that builds up of existing knowledge. And when Bartolomeo Cristofori built the piano, he had a background with harpsichords and with fortepiano. So he had probably something in his mind. And then he realized the piano, and that was, I mean, the hit, so the new invention, because it met some constraints that he had probably in his mind. And finally, these instruments got the result. He probably went through an incremental process of trimming, of trying, of mounting and mounting. And think also probably of Bob Moog, so when he designed the voltage control filter, so the super VCF that then became an heritage of the history of human culture. And I'm not sure that by observing the electrical network, so he said, okay, so we'll put some resistances here, then let's add 2 transistors here, the base, and then let us move this resistance, and then okay, so let us control also the feedback, and then, oh, super, then we can tune the resonance frequency and also move through the feedback, you know. So and so my point is, what's your opinion on the possibility to have some learning by doing So neural networks that probably the current generation of neural networks that try to build a new knowledge based on some knowledge base. But once again, how can this happen in the musical realm? So not on the viewpoint of building new sounds from existing sounds, but kind of building new instruments from the knowledge of previous instruments, like we did. So I think we, so there are sound designers, and that's great designers, but here I'm talking more of forging new sounds through the invention of new tools, okay? In a way that we do something new, we make something new by doing, okay? So how can we put the what neural networks would be able to do in front of designing new sounds with the concept of discovering new sounds through craft, through intuition, through objective knowledge of something like a piano or an electrical network in the case of Bob Moog, or a stringed instruments in the case of Stradivari, or the intuition of Adolphe Sax that he was thinking of something, and then the new sound comes up. So what's the future of artificial intelligence, of creative,
To be clear, you mean not having start from like a pianoforte and enhance for a new feature a pianoforte, but inventing a total new instruments?
Well, not total. Yeah, this is the point exactly. So we have a background. So I wouldn't be able to invent in something brand new. I should rely. I'm not coding something new. I'm thinking. I would try to do something by doing, not.
Well, neural networks rely on anyway. This neural. Maybe we have to differentiate between if you want black box or maybe some gray ones. But in any case, neural networks learn from the data set or what something already exists. You know. So at this stage, to create something new, we have to start from the data set to define where we want to go, where we want to maybe take some feature here or some other aspect from another side, and or we let the neural networks in black box manner, and we can as this is collected connecting with the works of the newer audio effects where we implemented different effects in one model basically. But if you carefully selected different things, different aspects, you can reach sounding that are based on from what exists, but not physically available in real life. Instead, on the other side, if you in the gray box, maybe is since neural network is a component of all the mechanism that generate the sound. In that case, you can tweak all the parameters that are available, manually available on at hands, let's say, and you can build. In this case of the piano, we try to generate based on physics knowledge, so the synthesis rules on that. You can change that or
Yeah,
you can train one and change that.
This is yeah. So yeah, we are getting the point. So would it be possible, in your opinion, say, to train a neural network not with sounds, but for instance with several sorts of electronic circuits, musical circuits, and see what happens once the network has been trained, yeah, with, say, a broad knowledge of musical electronics, or to train it with the tensions and the material and the length of a huge set of strings, along with the damping characteristics of the hammers, and see what happens, and actually, your thesis sparkled this idea. It's not. I mean, for instance, there's an interesting consideration here when you talk about it is. Yeah, I was also talking with Chumur during lunch, the fast lunch, and it is about the paper number 3. Now at page 87 in your thesis. Yeah, that is about, it is about conditioning methods.
Mm-hmm.
Yeah, page 87, it's a second paragraph.
Yes.
Yeah, and you found out that here you said in the discussion that the results indicate that conditioning methods perform better when placed at the end of the network. That is absolutely counterintuitive. No, I mean, you expected, of course, that if you have to condition because parameters change, then I would think to put something in the first layers of the neurons and not at the end. But for some reason, you found out that if you put them in the end, so. As if the network, in a way, elaborates the informational content coming from tweaking the parameters at the end. That is absolutely not intuitive. So maybe there's not a direct connection between this consideration and the previous one, but let's suppose to revert the intuition about how neural networks learn and why, and maybe train them with sets of different data. That's probably so. Bob Moog, he was an electronic engineer, so besides being a musician, then he invented the VCF. But my question is, do we really need to train a neural network with all the possibilities that a VCF has, and instead of train it with more objective data, more physically based data, and not musical based data?
These are definitely a path that you can continue on. I mean, in this case, it's like experimenting, or is maybe similar to sonification, where you take the data, you take material from something that is not audio or sounding. But in that case, the outcomes are not so immediate. It's about experimenting and with networks in various shape. I mean, you invent when you experiment at the end. So I think it's definitely possible. It's you can take materials from different aspects of our daily life and put together in a, of course, suitable way for the methods or for neural networks, and see what's happening.
And would you envision a possible work plan, a possible roadmap for suggesting some types of networks instead of others, and types of formatting these disparate data in various, this disparate knowledge, for if one would try to follow a way like this?
So if like tomorrow I say, okay, I want to try to create a new instrument. I mean, for the to start from for the technology point of view, I will select the type of network that I have used for my thesis. One, because suitable for time series, but also because if I'm with the aim to create a new instrument, I would avoid to create big generative modeling that are maybe difficult to play. So as I said in the introduction this morning, also these requirements I think that have to come immediately. So I will start with like state-based or neural network, recurrent neural networks or state-space model. Also because they allow very easily one-to-one sample and tweaking, having a weird connection. For the dataset, that is actually very variable. I mean, for example, we have taken 3 datasets totally different from. It's still audio, but was totally different. Audio processing, delay, distortion, one was just dynamic, and there is it's very let's say fun, like conglomerate data set and data. It's important to be consistent, label and synchronized and so on. And then from that, I would try to play it.
Yeah, I think having fun is one key. So you know what synesthesia is?
What a DJ is?
No, synesthesia.
Synesthesia.
You know synesthesia? A PhD student should know what synesthesia is. Yeah, even musicology, because it's a psychological concept. It is probably a key to creativity and the formation of new knowledge using the creative ways that our brain has to build new knowledge. And this synesthetic creativity that our brain has, depending on, it is a bit subjective, so, but it looks like synesthetes, so people who are more synesthetic. Well, synesthesia is basically linking one sensation in a sensory modality to a completely different sensation in another modality. So, for instance, to hear a note, and a synesthete person has, for instance, imagining green color. And if the note is different, not you, but depending, so the people who have synesthesia say imagine, say orange, and this can affect the different modalities. So look into a flower and hearing one sound, or looking at an image and smelling some flavor, and so it is a kind of cross-modal effects that are in people who say they have synesthesia. They are quite evident, but to different levels, all of us have some forms of synesthesia. For instance, maybe you know the experiment of the Kiki and Booba. So if I draw a figure with these angles, or another figure that is much more rounded, and I ask you who is Kiki and which is Kiki and which is Booba, so 98% of the persons associate And these associations are the base of creation of new knowledge. So our brain is able to build new knowledge by capturing from different senses and putting together things in a way that are, for many reasons, they are creativity has a correlation with synesthesia. So my last question was, I think it's my last question. Yeah, definitely, it's absolutely my last question. Is that is pretty speculative. Is and you said the magic word. So having fun. So probably using different types of data and try to imagine a neural network that is able to creatively, in a way, connect different forms of knowledge, but concretely, I mean, then could come up with some more speculative but in our case, it could be imagining it to design new sounds, but not just by starting from an enormous set of sounds that is non-synesthetic in a way. So that is from audition to new knowledge about audition. That is not exactly what we want. We want to have in different aspects of so there's the sound, there's the sound object, there's the instrument that produces the sounds, there's the parametric use of a digital sound effect, and all these things together probably contribute to form new musical knowledge. So my last question is, would you envision a scenario in which neural network can turn useful, maybe to support the designer, the sound designer, or the musical instrument maker in building something originally new?
I think so. Yes, I will go with a yes. Also, you create something new with something that exists. So this is also a good point for neural networks. So we cannot just we can extend this also to a broader musical context, like agents or neural networks that play with you, that interact with you with not a normal, normal human interaction, let's say. So I think that in the future there are already say studies or work on that. Neural network will support for sure the developing, or there are some also commercial products that try to give from neural networks newer sound. Since also is like you give a neural network, you give a data set, you don't know actually exactly what the neural networks do, and this is a good problem because we have like something that is not clear immediately to you, that is how to be, but help you to I'll say mess up with the cards. I would say like I don't know the English term for that.
Scrambling.
Scrambling the cards, can that help you to have innovative or newer idea, newer sounding, newer interaction with that.
Okay. Yeah. So my last two questions were a bit to understand vision, because I think that PhD graduates, as you hopefully are going to be, have to keep vision. vision. Otherwise, we just rely on neural networks and let them do the job. But no.
Yeah, no,
We have
definitely not.
to keep vision. Okay.
Thank you.
I think, yeah, my opposition is over now.
Thank you, Federico and Riccardo. There is no more break again in 15 minutes. And should anyone present wish to speak as an opponent ex auditorio, notice should be given to me in the break. There's some leftover sandwiches and coffee. Please help yourself if you're hungry. And then these proceedings will continue at, 15:05. We will... upon the second opponent, Associate Professor Chumu Erkut.
Thank you. First the clicker, and then we made the plan, several plans actually. One plan is that we can switch back and forth some notes, some ideas on that. And second plan is that probably Riccardo will have more FaceTime, more to talk in this part. That we could talk about some reflections and some discussion about your thesis. So let me start with the most important thing, the first half finish, the vision about what we're doing and why we're doing that and how are we dealing with a state-of-the-art constantly changing, how do we promote our contributions in that. So that's a challenging thing. In your generation, many papers are coming per day, about 150 in audio machine learning to archive. So how to really emphasize your contribution, I think will be our primary challenge, and what this contribution is. Okay? So this is my most important part. The others is just supporting material. These are the 11 papers we find in Riccardo's thesis, grouped as he did in maybe 3 different chunks. The first chunk is getting some virtual analog devices and modeling them with machine learning in a digital way. And the second part is working with piano, which also I will mention that. Some of my dream problems solved here. Very good job on that, but we're going to come back to that. And the third part is, for me, very unique approach to generate data which we absolutely need for reproducibility, and also trying out several extensions of that. So our plan is how to highlight this contribution and how to give it to the next generation which followed you, your knowledge, your code, whatever material you have, your data, so they can tackle their dream problems after your exploration. For me, and the material we'll do is, I ask you to do that as well, that maybe we should go to your repos and support pages on doing that. The easiest start is this one, because it is unique and it's repository, the code base, not only the scientific work, scientific contribution you have, but also the actual tools, actual code base, how it's done. So for me, maybe you can now go to the repository of this one. That's the last paper in your thesis, and we need to press also the button that we can
yes, sorry.
show the audience. Okay, so technical problem.
No, sorry.
Okay. So while you're doing that, I'm starting with that because it is, for me, the most mature code base. And there's no precedent. I don't know any other work on that to go beyond the state of the art. So that sets the state of the art. And the repository you have is a graphical user interface, pointers to the scientific references, and a very clear instruction about how to take this tool and apply it to your problem. Actually, it has 2 components and addressing both aspects of your exploration. So a little bit above, you see, can you just roll it to the beginning of the thing? Perfect. So here, what is it, what it requires, how we can download it and make it work. And these are the releases. Usually the contemporary work, when you go a bit more up, contemporary work works with all these things, explaining this, the code base itself, but nowadays we are using a lot of material for continuously compiling it, making ready as a package as well. So this became the contemporary way of building our tools, right? So this is a great example about how to make this kind of rule, how to immediately get your results to other people that they can try, and where they can get the more information about that. And with the last screenshots, what the tool is about and how it will work in the environment. We need to do that because there's so much competing platforms, there's so much competing structures, approaches, that we need to be sure that it will deserve the time we put into using that tool or extending tool. So this is a great example, your last paper. I think it has all the lessons learned. So this is our starting point. How did you come up with this idea to make something like this?
First, we have to say that this idea is almost. We have to thank my supervisor Stefano. This is the first author of this paper and is also enhancing this tool. Maybe I don't know if you saw, but for the synthesizers, yes.
Yeah.
Yes, sorry. So this one was to solve a big problem that is the retrieve dataset, because of course, again, to train neural networks, datasets are a crucial aspect, and also it's time-consuming process. The difficulty also start from include also when you go to a physical instrument or effects, the time consuming, the time to record all this and all the parameter combination. And we have like a good example for the compressor that have not any indicators on the parameters. So you have try to be very precise on move all the parameters so on, and a lot of time. You don't have so much time to do with all the machines, but you need like data set that you need to validate your model, validate your path. So. Also, another point is at the beginning was difficult to, is not trivial to decide what to put in the audio content. You can't record hours and hours and then train the network because you never finish. So there is a lot of trial and error, try to change the content of the audio, so on. And this was to solve this big problem. In this way, you have like a patch that can automatically. You start from is a digital data set, but can help for the previous stage of your work and so on, and allow you to synchronize, perfectly synchronize waveform. That is fundamental in this case. Automatize all the recording of parameters with all the resolution that you want. Offer additional features that are very difficult without a robot, let's say, like the sweep. So record the parameter while it's sweeping to see how the neural network is actually responding on a continuous changing. It's. I think it's a great tool for all the research, that have too fast, let's say, the design and the first stage at least of the design of the architecture. And
I certainly agree. So this is C++ a bit, Max and JavaScript most of the time. It works in Max MSP, and everything is very clear here. So to wrap up our discussion, this is a specific dataset tool because dataset management in neural audio processing is a pain point. We don't have this dataset like we can go and download from somewhere. There's some good examples happening, but usually we need to create our data, and it simplifies these tasks. There's no modeling or neural networks involved in that, but you always have in mind that there will be consecutive training of a model. So therefore, it also solves the pain point of combining the data with a neural network and trying further. And it uses the best principles of the coding, which software engineering says that this part of the continuous integration, continuous development that makes software life cycles very fast. So this ticks all the boxes, and great piece of work right here. So let's go back to the first group and see where we are with that. The first group, no, this is the previous one. This is exploration. The first group is about the virtual level.
Yes.
My first question there. So here, what is, your thesis title is called Numerical Modeling of Musical Devices, and then you're for efficient and low latency data-driven emulation of nonlinear time invariant. We talk a lot about that time variant cases. But if that's your problem, I would think that the actual output you would think would be a plugin.
Mm-hmm.
Do you agree?
Yes.
But you're
No.
not doing that.
Yes, the plugin was one part of the. I selected the TensorFlow framework in order to have like actually a faster plugin transport, but and it's something that actually I show up in conferences as a demo, but for time constraints I never release a real BST.
But it's just the time constraint.
Also, it's time consuming to debugging and find the right to integrate a neural network on.
You're really this close.
Yeah.
I mean, the original paths go to your training that you did, but after that you change everything to, if you're working with Torch, to Torch script or Torch Lightning, and if you're on TensorFlow, then you use TensorFlow Lite and everything. It compresses, serializes the model, and you really can put it into the plugin, which you can also try it in command line. So we discussed that that would be additional 1 hour or something for each work to try that out.
Well, 1 hour because I tried,
Okay.
but I use a CPP flow additional library to infuse the model inside, and I had some results to do with the demo, but I never wasn't able to compile in a proper way. I had to spend the time.
Okay. That will bring us
This is actually this stuff is a pipeline that I was also considered to do in this year, because for the thesis I prioritize other works.
Okay.
But it's not something that I totally neglect or I didn't think about.
Okay, there will be continuation of
Yes,
your
yes. No, this is also because we are me and others are aiming to amplify and help to continue the RNT neural network, because to include my model, the state-based models and the encoder-decoder models that are not wasn't supported at the beginning, and at the end this is an outcome that is expected. But for the aspect of the thesis, we prioritize the count of the flops, other more measure and precise measurement.
Yeah. Let's break down for the listeners. So what Riccardo does is he looks at the simulations, training, and then he counts the operations about if he can run that in real time, which gives a very good idea, of course. But nothing beats to put that into the memory stick and give to the music producer and ask how many of them you can run in real time. That would be the actual information. If you're getting 4 of them in real time, that means that it is 4 times the real time that it can afford. And we started this work with when the second part of the model, not maybe the first one, came out. It wasn't real time, then it got real time 1, then it got real time 2, and some recent things are claiming 27 real time, that you can have 27 of them working at the same time. And the first is a simulation, the other is actual production thing. I think with your kind of background institution, I would expect to make that step as well and check. But I'm happy that it's going to come and you're going to do that. And another thing, so what is the state of the art that you wanted to beat here?
Here was, because when I started with thinking about the compressor, mostly work was on distortion, and some starting work was for the compressor, but was the temporal convolution neural networks that was taking, had some limitation on their activity. So we wanted to enhance, try to enhance the neural modeling for devices with temporal dependencies with attack release, but keeping a small input window to.
Okay, so you're saying that your state of the art was Vesa Velimaki, Alec Wright, and that team's work, which started in 2020. That was your.
And I think it started before. I think that the first work on neural network was 2015.
Yeah. No. Davide Rochesso had a 91 paper.
Yes, right, yes. Was.
I have a 97 paper, but.
Yeah, but the.
91, no, 95. I'm in 97. But the thing is, I mean, earlier approaches had a different background. When it comes to the classical approaches, your references says that there are several teams are looking for small networks from the beginning. They're not looking at large networks that, for example, Google uses for speech synthesis, WaveNet and everything else. But they're looking at the small networks because they are thinking about real time from the beginning on. And they're using to train these networks, then condition, and then do all of the things. And I agree with you. That work already goes back to 2015, maybe. It got a high point in 2020, and at least Vesa, who is my supervisor as well, and his team published that quite frequently. You visited them, right?
Yes. I was doing the master with Aeropeka.
Yes.
Was the first one.
So they have some resources to do that. They streamlined the process. So for them, taking another instrument and going through the process is almost a streamlined process. And they want to highlight the contribution quite nicely. But the state of the art came to a so interesting thing, and I don't know I don't expect that you know that because the paper came out 2 weeks ago after you submitted everything, but while you're preparing. But did you hear about Nabla?
Yes, actually. I didn't have time to read that paper because I downloaded. I saw that came up some days ago, basically, or some times ago, and I didn't.
It came to archive like maybe 2 weeks ago, but then the code is available as well.
Yes.
Immediately became a state of the art for the reasons that we're going to discuss.
Okay.
So let me not this, but this. This is what they do. This is the Nabla FX paper, the code. This became immediately the state of the art in what you're saying. You came close to some of the things. It has the DDSP that you work in the second part as well. It starts with the Spotify's pedal board that just makes black box version of the several effects without going to the virtual analog. But as you see, they are checking if the model is using differentiable structures, meaning that if it's just given the effects, or if you can give examples and understand the effects parameters as well, then it is checking if that uses neural networks. That is, is checking if it supports the processing work. So your approach at the model ticks this. And then can you make a control conditioning? You tick this as well. And can you define chains? Can you make several modeling blocks one after another using the approach? And can you make is the key, meaning that they give you Lego tools, like LSTMs, temporal neural networks, not space approaches or different structures, but they give you a choice of 4 different neural networks. They give you a choice of film, as you also use, and different conditioning things. So you are mingling them to make your approach. And that became the standard of the art immediately, because like in the second part you did, they give you a tool to try out lots of different things and combine with the best software approaches available to make that all the way to the plugin. I don't expect this is too new for you, but let's look at why it is important to do so. Am I clear, or will we deviate a bit from the subject?
No, continue.
Yeah, so in general, we have one approach, which is the first, maybe Vesa's laboratory that you visit. You are concentrated on the problems to solve. Here is my new device. I'm going to model this. On this, there are some unknowns, and I'm going to simulate that and solve this problem. When I finish that, I leave my code like this. Because it solves the problem, I don't need to make anything else. I switch to the next problem. Maybe I copy my code, build upon this. But this code and the next code, this problem and the next problem, are separate problems. And it works perfectly for scientific dissemination. Another problem is another paper, and we're learning and putting the things, and that's the approach in your thesis, which worked quite okay. I have no objections. It's within the scientific method and works perfectly. But if you go to the tool base, which will come in the DDSP and RAVE in the second parts as well, this kind of models, then we are going to a different level, which we can maybe remember from the current foundational models, large language models. Okay? These problems, these approaches, these toolboxes are trained with vast amount of data, but they solve different problems using just combination of what we have. And this foundational modeling that the ChatGPT and other language models are now applied to the audio. There are Meta's audio box, which also, again, 2 weeks ago or 3 weeks ago, they released the evaluation package, meaning that you have some listening test in your thesis, you wouldn't have to do that. It will predict the listening test results of a large amount of subjects. So this is getting to that level. To understand your contribution, you maybe work with a larger toolbox, and you're putting all the elements together to solve your problems. And my thing is, because of the planning, your contribution is not at that level. You are in the different problems level, which we found very acceptable for a PhD defense, but are there any things right in the near-term future that you can adopt this approach and solve different kind of problems in a sustainable manner? This is the main thing I want to investigate right now. So we came here a bit like complicated way. I hope you're feeling okay on
Yes,
this.
yes.
But let's see how we're going. And needless to say, Nabla FX is coming from Joshua Rice Group, Christian Steinmetz,
Marco
and
Comunità.
Comunità.
Yes, I know.
They're doing this, and it ticks all the boxes, yeah? So there is everything there, and providing an analysis for black box, gray box, white box modeling, for different type of problems with different data sets, and all the tools we require for solving these problems efficiently now included into that approach. And let's go back to the last group, this part. Now you're looking at a complicated acoustic instrument, and you're learning a lot about its physics as well, but you're using neural networks to simulate all this. And in my view, you are working on the DDSP code base, which was so influential on me that I really, when it came out in 2019, I said, okay, now I'm seriously looking into that. I don't do a lot of other things, no virtual reality, no augmented reality, but this is good. So this is your approach, which was very successful in the beginning with DDSP, but also it evolved to a different direction. Before going that, let me acknowledge we had a lot of time in this paper together. I was the associate editor of that paper, and you had a reviewer too, like this opponent too, which was very critical of some things, but you managed to explain and improve the paper, which was very good. But my favorite on that is this, because for the first time you're solving an unsolved problem in this group. Nobody could model the transients before in this context. There was a model synthesis approach which looked at the transients, but you used DDSP in the beginning, extending it to fine-tuning from your problem. So this is very good point to start to tackle this kind of problems. Okay? But let's go to this slide. This is the DDSP structure that you start, the base structure. Okay? It has a differential component. We understand its blocks, and it is immediately applied to timbre transfer problem in general. So it is not a particular instrument, this or flute or violin, but it could do a lot of things if the assumptions are working with the what it can do. This is again way back Xavier Serra thesis about science and also noise modeling.
Yeah.
But Xavier Serra's thesis also didn't have anything on the transients, pure DSP, no machine learning. But a PhD student from Karma called Tony Verma provided the first discrete cosine transform. You're referring to his paper and everything. So you know the story. But nobody could do that with the neural networks. You're the first one to do that. But that was the code base. It started like an analysis tool. They were giving you some code base to train your own model. Training means you would either use Google Colab, which will kick you after 1 hour for training that. You are saying that an instrument was initially requiring half an hour. It reduced to 13 minutes for an instrument database to be done. But the training took longer a bit. And we didn't have the infrastructure. In your thesis, you're outlining your infrastructure in the beginning chapter. It's quite good infrastructure. So you're using a lot of resources to solve your problem. There was a table about all the infrastructure you used for your thesis. And it's quite good. So you're solving similar problems, but while you were doing that, look what DDSP did. They released their first plugin after a year of doing that, putting all this real-time thing in a plugin that it can be done, it can be executed in real time, and they provided the tools as well. And meanwhile, for me, if we can ever talk about a foundational model for this kind of approaches, that we can understand musical acoustics at the same time, although the model is complicated, for me that is more rave than the DSP at the moment. You can have a different opinion. But rave is also directly aimed for both plugins and embedded platforms. And they have a heavier training chain. but they provide the state of the art. So if I would choose a state of the art to beat for this kind of problems, I would probably choose Rave now. And so are other people. But DDSP is still good because it's more explainable, more understandable from the diffusion models that you taught. So based on that, let's come back to your contribution here. You started with the DDSP base model. You extended each of them on, to solve particular problems, more intricate problems. We saw lots of demonstrations here about how the coupling works, how the musical things work. And you successfully provide solution to all of that and scientific contribution. Now the killer question. Compared to the first repository that we saw, what can you say about the state of the repositories in this group and in this group?
Yeah, I got the point. It's less descriptive and handy, I'd say.
Yeah, you are just doing what you promised. You're solving the problem, but if you land on their support pages or repos, they even don't say what we need to do to run the model, right? They don't say, like, unlike this paper, which gives every information to reproduce the experiment, I don't have a requirement in most of them. I don't know how to start coding and using your problems to solve that. They're convincingly given examples that, yes, this problem is solved, but you're also not putting the summary of that. So I made an exercise. If I can put everything in a single slide, your contribution, everything, models, code, data, main contributions, control, like the matrix we saw, it looks possible, but also we don't have it both in the thesis and in the contribution page. So if you want to really work on that, my first suggestion would be your main support page. There's a list of repositories now. Let's extend it to immediately show what you did, what is your unique contribution in the thing. Not by text, but very, very graphically, like you do in that thing. So that would be a suggestion. And let's maybe conclude. We can go infinitely about several choices, about what blocks that you're putting, but that papers are already reviewed. They pass through a journal and conference thing. I don't see a big point of elaborating if some kind of a newer structure would work better on that as well. I take that you're solving your problem, what you need to solve, very, very nicely and efficiently. Okay? But what I wanted to say is this part. Now let's go to the slides and let's make a dialogue of it.
Okay.
Do you know Scott Hawley? He's working at Belmont University in Nashville. And he is a co-founder of Harmony, I think. All that stable diffusion and everything are coming from their code base. Now they recruited a lot of people. So he said that in 2021, during the COVID times, he said that in audio processing, we make a lot of model development, data analysis, and these are the key activities that we're doing, but we should make more tools to make everything much easier. I extrapolated from now on, looking at what's happening to the other sides of the data engineering, and immediately some software development processes came into the play. My suggestion would be, this will be important for the future for our field as well. Lots of companies and lots of laboratories will look of people who can do more things with the models. Okay? So that is my propaganda since then. Whenever I went to a conference, whenever I was invited to a talk, lighting talk, I tried to make this point clear, that we are solving the problems, that's a transient phase, we need to do more. Here is the summary of our discussion two ways. First of all, in your approach, the modeling approach is the prominent approach. You're solving your cases by adjusting your model, extending your model, and then you're creating nicely, not lots of people are doing that as well, your data structure. But the way to do that with code although it solves your problem, it can be made much more efficiently to communicate. And model-centric approach, this is one definition of machine learning. You used another one, but it encompasses everything you actually do. Okay? So this is what we have now, and that is how it should be. All these approaches are only here, but all of the peripheral needs to be also done. Automatic testing, data version control, model version control, probably that would be required in the industrial deployment and more in the academia as well, right? So we have these kind of things, and several Google's DDSP type of approaches, when they go to tooling, they're taking more and more of this kind of things. My focal point will be deployment and reproducibility. And the solution of that is really to develop the plugins, in my opinion. Okay? So, are you familiar with this? This is a very influential paper in software engineering related to machine learning.
No, I didn't think about it.
Yeah, it created an entire field of taking DevOps approach in software engineering, meaning focusing on continuous integration, continuous delivery, automatizing the code, to the machine learning platforms. And they introduced the technical debt. Meaning, if you don't do that, you are building some kind of debt which will come to the future projects. And I learned that by experience, just receiving 4 terabytes of graduate students' work, which I cannot do anything. I had to throw it away, all this training. Maybe your experience would be different. I think you have a more structured approach on that. But just know that this model data triangle is this part of machine learning, and they claim the whole ecology is the future AI engineering, so to say. Do you agree?
Yeah, I mean...
There are lots of critics of that approach too. But it's an influential approach. So what's your take?
okay, so...
You worked here a bit. That's good.
Yes. Like I would say that there's a lot of, as you say, a lot of aspects that are not fully covered or not fully developed in a proper way, etc. And developing at the end tools like VST, etc., is valuable and something to do to complete the circle. But there is also the time constraint
Yes.
feature that in a PhD
important.
is very critical. And I think that not always is easy or possible to do all everything, all the ecosystem alone or in a limited time frame. This is the one of the big challenges also that I face myself because you read the results, but on that there are a huge amount of training times and testing, design test, etc. And I think that the practical part, the industrial, not the industrial, the part that go more to the tangible things. I mean, in my work I left at the end, or anyway, as at the end of the pipeline. So I agree with that is important ecosystem, but my big point is the time constraint of the work.
Yeah, I clearly see that. And you started with, of course, that's an ideal case. There's no ideal case. It all depends on the problem that you're solving. If you're solving a problem in a huge time constraint, then you go as direct as possible to solve your problem. Same thing with the medicine. If you go to emergency service to keep you alive. They can break your whatever rib cage.
Yeah.
It's not a very nice approach, but sometimes it's necessary. But while you're doing that, just know that you're borrowing from the future. So here, lots of different things we can discuss. But let's about this one, monitoring, the data monitoring, model monitoring. You made this wonderful tool, the 11 tool, which goes and extracts all the data. Then you can have a future extraction if you're going to the classical smaller models as well. Let's see that maybe 2 months after that, they change the plugin. They release the next version of the plugin. Your data is old. It works, but it's not the recent data that the whole thing brings. So that makes your experiment unproducible because there's no relying data. So this is all a chain that when you're efficiently solving a problem, you're also maybe borrowing that from the future. And here are some tools that can be done, including embedded platforms, including lots of approaches that can be used for this. But I'm not going to spend too much time on that. That could be when we would go to the plugin. And the difference is probably, besides the normal plugin development, that at the moment we can pretty much automatize this part. Machine learning approaches also provide a model file that the model needs to read. Okay? So this is getting easier and easier to take that model file and combine in the audio plugin. So this tool chain is increasingly getting easier. That's the ESP. That is how Ray works as this. Meanwhile, we're doing a lot of contributions to the knowledge theory. Ray wouldn't happen if we wouldn't have a streaming real-time cached convolutions. So there are always new structures coming there, but they're enablers of the whole thing. But I want to come here and maybe the next slide, the same approach. So this tool is interesting because it already gives you a lot of material from that infrastructure. The first thing it does is it integrates weights and biases for model training. Did you ever use weights and biases or other ML flow kind of services?
From other models or?
For in your research altogether. So here is the thing. You are working with a few thousand parameters model. A large language model is 1 billion parameters.
Yes.
Plus you have the hyperparameters. You're constantly experimenting what's the best approach.
Yes.
Sorry. Think that you're successful, you understood a good parameter, hyperparameter set. But of course, this is working good. Which data part gave it? Which model part resulted in that? And can you retrieve the experiment in a couple of days? These are the questions that this kind of integrations address. Model and data lineage is what they're monitoring. So now, state of the art is continuously integrating these tools, monitoring tools. And here, there are different systems included in this. Here are different conditioning parameters, TCN, elliptics, and you can deviate the metrics. So my suggestion would be, if you're ever going to look at that, these tools are becoming more and more available, and also understanding where are we with developing some analytical tools. I don't want you to read all this about this, but these are analysis tools about how individual groups are approaching that problem. In essence, they're implementing this.
Mm-hmm.
In each part of the thing, the whole idea is make everything we can automatic, that we don't lose with manual copy and pastes, manual taking the weights from of the model. We use all these approaches to make this happen. And that would be my suggestion, to also look at that aspect, to make your code base also valid for different problems, different approaches, different data sets that you don't have to manually fix every time. And you are also promising that to the next generation, right? Because when they embark another PhD, they will build on your code. So let's give them some tools. And in my opinion, so we talk about all of this. This is weights and biases. This is actually Anders, a PhD student at that university, working with his problem. And in real time, I usually see what he's working on, what results that they get. These are free for industry and academia, I'm sorry. So we have not too much excuses anymore not to integrate this. We can do that with workshops and everything. So in my opinion, all this discussion is to point you probably the only weak spot in your thesis. Other than this, all these 11 papers, all the results with several significant contributions, like the transients in the sinusoidal DSP type of models, like the hyperconditioning functions coming from other paper. These approaches, these results are very good. And your work in this thesis is very significant as well to solve that problem. So all this time, I just tried to show a single problem in the thesis. And you have a means to solve this maybe and give your thesis in a better condition to the next generation. Take it or leave it, I don't know.
Oh, sure, I will take it.
But in my opinion, we will go to the conclusions very soon. I think all these papers and all this work is in super quality. Otherwise, as an academic work, it is great thing. So with that, do I have anything else? No, we come back to this. But let's go to your pages later on, after the thesis, after celebrating and accepting conclusions. From this point of view, is there enough information that I can extract all what to do from your companion pages? And this should be the last. Yes, indeed. I don't have any other questions. Do you, Kev?
No. Thank you very much. Thank you again.
Thank you. Does anyone want to speak as an opponent of Solturi? Since that does not seem to be the case. On behalf of all the Faculty of Humanities, I would like to thank the candidate and the evaluation committee for having carried out the disputation ceremony in a critical and challenging manner. I now declare that these proceedings are over. A report will be made to the board of the University of Oslo. Disputation is hereby concluded. Disputatio peracta est. You will arrive, you will find.